So today we're going to talk about AP Physics C. I think 2 weeks ago, if I remember correctly, we kind of talked about AP Physics 1 and what type of problems we'll see on there. Today we're going to talk about AP Physics C, and more specifically the mechanics section. AP Physics C has two tests. It has mechanics and it has E&M, which is electromagnetics. So let me get the slides up and okay. So today we're just going to look over a few problems in AP Physics Mechanics. For the most part, AP Physics Mechanics, the concepts and like the materials are very similar in terms of like basic ideas for AP Physics 1. However, a stark difference is that it's more complicated and there's also a lot of calculus involved. Yes, you have to know calculus before you start this because you even from the very first unit, which is literally just distance, speed, and acceleration, they will start the AP Physics C's where this stuff aren't just like constant numbers. They can vary with respect to time, and in order to be able to find the transfer from like one property to another, for example, from displacement to speed, you have to do operations you would find in calculus, which for distance to speed and for speed to acceleration, that would be the derivative. Um, it's your choice whether or not you would like to see me go over like the actual calculus in these problems, or if you just want me to like brush over them and just go over the major concepts. I have no problem with either. If you want, you could just type in the chat for like which one should we do. Yeah, like the basic procedure to solving the problem. That's kind of like what I mean by concepts. Yeah. Okay, so we're not going to go too deep into calculus since I don't think you guys know it yet, since you're not in high school. So the exam is 90 minutes and it's split evenly between multiple choice questions and FRQs. Each section is 50% of the score. And for each one, you have 45 minutes. The multiple choice is 35 questions and the free response is 3 questions. Although for free response, those 3 questions always have multiple parts to them, normally 4 to 5. We're gonna look at this one is kind of like an example of what a free response question will be like. It's extremely important to pace yourself and never spend too long on a question in Physics C because the test goes by extremely quickly and the questions are quite hard in terms of concepts. So there are definitely going to be a few that you will not know. It's more important to try to do the questions that you do know and can be relatively sure that you got correct. Because the curve in Physics C is quite generous since most people don't finish the test. When I took the test, I didn't finish either. So yeah, it's more important on trying to be confident on what you do know and just skip the things for like what you don't know because that wastes valuable time. Well, anyways, let's look at a few like actual like conceptual stuff. So we have 2 cars that are on a horizontal level track and friction can basically be ignored. Cart 1 has a sensor that measures the force exerted on it during collision, whereas Cart 2, and that Cart 2 is the one that has a spring attached to it. Car 1, this extra part that you see in the diagram, that's just part of the car. Car 1 is moving with the speed of, sorry, it's moving with an initial speed of 3 meters per second, and it collides with Car 2, which was initially at rest. Um, the total mass of cart 1 and the sensor is 0.5 kilograms. The mass of cart 2 is 1.5 kilograms, and the spring is basically you don't have to consider the mass. The spring does though have a spring constant of K, which is 130 newtons per meter. That's basically the elasticity of the spring. How well does the spring bend with respect to force? Um, the data for the force the spring exerts on cart 1 during the collision is shown in the graph. And a student sees this and models the quadratic equation of fit, um, F as F equals 3,200 minus 500 T. So it's 3,200 T squared minus 500 T. So how you go about solving this is basically as follows. Part A, um, asks for the total impulse delivered to cart 1 during the collision. And impulse, if you're looking at a force time graph, is the integral of the function. That basically means that since force is applied over time, in physics 1, you'll learn that since force would be constant in like momentum problems, you would learn that it's force times time. And that's how it works if force is constant, because uh, the integral of like some constant c with respect to like a variable x is just cx. So you are just simply multiplying by time. Here, the force is not constant with respect to time, so you actually have to get the more general way of finding impulse, and that is through integration. So what you would do is that you look at this quadratic equation and you would integrate it. And integrating oh, sorry. I don't know when it muted, but okay. Did you hear like me explain the problem yet, or was I muted when I was explaining it? Okay, I talked about the spring, and you probably saw like the first part, so I'll continue from there. Impulse, if you learn in physics 1, is change in momentum, which is the same thing as force times time. Now, here force is not constant, so impulse has to be the integral of force versus time, not just multiplying it out. And integral is basically finding the area under this quadratic equation of fit. So you just look at this parabola, and with respect to the x-axis, you find the area of this curved figure. That will give you your impulse. In terms of finding, it's usually quite important to try to do part A before most other ones, because it will typically be the easiest of them, or it will give you the most important information. So here it would be probably the most straightforward of like the parts. Um, Even if you can't do part A, if part B just uses information you found in part A, that the question just says, oh, you know this, or you're trying to demonstrate this in question A, you still do part B if you can, because first of all, they don't dock points for not getting like previous parts, and second of all, that reduces wasted time. So anyways, the solution for this is finding the integral of force with respect to time. So you take your quadratic equation for force, integrate it from 0 to 0.16, which is approximately when um, the function hits the x-axis again. Here you use your power rule, and you use the second fundamental theorem of calculus to try to find your bounds, and you'll get your total impulse delivered is negative 2.03 Newton seconds. Okay, the next part is to calculate the speed of cart 1 after the collision. Now, how you would do this is that you would use impulse momentum. Impulse momentum is basically just saying that your total impulse is your change in momentum. And momentum is mass times speed. So here, since we're just trying to find the speed of cart 1 after the collision, we are trying to find like the total impulse that's delivered on cart 1, which was basically what we found earlier. That J value we found earlier is the impulse delivered to both cars, because momentum is generally conserved. So by Newton's third law, if some force is applied to like one of the cars, it must apply to the second one in the same way. So here we're just going to analyze cart 1, and you would just come up with your equation J equals delta P, and that's J equals M1 V1F minus M1 V1 initial. And then thus you just isolate VF by dividing by M1 and then adding V1 initial. And we already know all of these variables. J is negative 2.03 from the previous part. M1 is 0.5 and V1 is 3. So you'll get V1F is negative 1.6 meters per second, which kind of makes sense considering that one car is at rest and one is traveling at the other way. And the collision basically will probably, since the second car is heavier, will probably let the first car bounce. If you like could imagine this experiment happening, it kind of like causes the first car to bounce backwards. So that explains why the speed changed in sign. Now, the part 1.2 asks which direction does cart move after the collision. We just kind of discussed this. It moves left because we kind of defined, it was kind of like defined in the problem that having a positive velocity was moving right. And by like the previous part, we just found out that cart 1 moves at a negative velocity with respect to right, which means that it's moving left. Calculate the speed of cart 2 after the collision. And you could basically do the same thing with the impulse momentum equation, except you're only analyzing cart 2. So you still have your M2V2, and that's equal to negative J because the force changed. The forces are occurring in opposite. So you have to switch the sign. M2V2F is equal to negative J, so V2F is negative J over M2. And then we already know what M2 is. That was given the problem. We found J earlier on, so you can just divide, and you get that V2F is 1.93 meters per second. Am I going too fast, or is this pace okay?
I'm okay with that.
Okay. Part 1.3 asks to show that the collision is elastic. Now, an elastic collision, since I've kind of like talked about this before, I'll just go over it quickly. It's a collision in which there is no loss in kinetic energy. So what you would just do is just use that definition and try to find the initial and final kinetic energies. And if they're equal, that means the collision is elastic. So K1I or K1 initial is just the kinetic energy of cart V1 before the collision, and that's since cart V2 was initially at rest. And afterwards, you just find, since we know the velocity, you could just find the kinetic energy for each cart and add them. So you can see that they did this below, and they plugged in all the numbers for like the 1/2 mv squared equation for kinetic energy. And if you evaluate this by calculator, since you're always allowed to use a calculator, you get that these two values are pretty much the same. So the collision is basically elastic. Calculate the speed of the center of mass for the two-card spring system. Um, so here what you would use is conservation of momentum. And because throughout the system, momentum is conserved, which means that the net momentum must be the same as the momentum of the center mass, and all you have to do is just find the mass there. So you have m1v1i, which is the momentum of the first cart 1 before the collision. And then at that point in time, it was the momentum of the entire system. Now that quantity shouldn't have changed. So the center mass can be like expressed as just the total mass, just m1 plus m2, then times v, where v is the speed of the center mass after the collision. Um, so you just rearrange the equation, plug in your numbers, and you'll get it's about 0.97 meters per second. Part 1-4 asks to calculate the maximum elastic potential energy that was stored in the spring. Now, you can't forget these kinds of like fundamental laws in terms of like how objects behave. So conservation of energy will always happen unless there's an external force applied that results in change in work. That's basically the only way energy cannot be conserved. Just like conservation of momentum is conserved unless there's extra force, and how angular momentum is conserved unless there's extra torque. These things should always like be conserved. So here we have to use that because we know that at some point during the collision, cart 1 pressed into cart 2 that resulted in maximum compression of the spring. And at that point, when the spring is compressed at its maximum, that's when we are at maximum elastic potential energy. So you just build your equation, Ki equals Kf plus USF. And you can just use all of your quantities. Since we know what Ki and Kf are, we were trying to calculate that when we were trying to demonstrate elasticity of the collision. So you could just use the same values and subtract. You get US is approximately 1.52 J. Okay, so normally there's always a question in physics C, like question 1, where you have to analyze a graph or where you have to draw a graph. Likewise, there's always a question normally where you have to use some property of rotational motion or rotational dynamics. And this is kind of like one of, wait, no, kind of, it's kind of like one of them. A triangular rod has length L, mass M, and a non-uniform linear mass density given by the equation lambda, that's the Greek letter for L, is equal to 2m over L squared x, and x is basically just the distance from one end of the rod to your defined point. Here you can immediately see like some kinds of like foreshadowing, you can say, a warning where you have to use calculus, since we say that there's a nonlinear mass density. The fact that they're giving a function for density means that you'll probably have to integrate this at some point during the problem. Otherwise, they wouldn't include it there at all. That's just a waste of effort. So, and as you can see, we have to do integration. Using integral calculus shows that the rotational inertia of the rod about its left end is ml squared over 2. Now, there is no formula for rotational inertia of a triangular object. So you actually have to do this the hard way. And how you do that is you have to do you have to use the fact that the rotational inertia at a certain point around a center of rotation is mr squared, and you have to integrate that with respect to mass. So I is basically integral r squared with respect to mass. And here r, your distance, is the same thing as x, like the distance from the center of rotation your point is trying to be. And you can use here, since you cannot ever integrate with respect to mass, it normally either has to be length or time, and those are really the two conventionally accepted ways to integrate, like the properties you can integrate with respect to. So you actually have to make that dm into something like dx or dt, something like that. Okay, well, thank you. So you have to turn that dm into dx, and how you just do that, since we know that the relationship m over L was given by lambda, that's your linear mass density, we can just rearrange that to become m equals L equals lambda x. And obviously it's not an exact multiplication, we have to integrate it because lambda is not constant. So you would do just that. So you'll get integral of 2m over L squared x dx. And then you can simplify that, and then add in that x squared. So I is equal to integral 2m over L squared times x cubed dx. And then obviously the bounds for this are from when x equals 0, which is basically at the center of rotation, to when x is equal to L, which is at the edge of the rod. So you use the center of you use what was it called? A definite integration with bounds 0 and L, and you just subtract and you get ml squared over 2. Eileen, are you there? Sorry, I can't see. Okay. Sorry. Okay. I'll continue. So that's part A done. And normally the calculus is the hardest part, aside from like some conceptual stuff. So once you're done with part A, or like the calculus part, things will typically be a bit easier as you're mostly asked to apply this information. So here is basically something similar. Here's a hoop that has like rods that are stretching to it, and they are stretched evenly around like this circular hoop, and they're all identical to that rod from question 2, like that last part we did. So they're asking you to derive the rotational inertia I total of the hoop rod system, this pinwheel, or like this Mercedes-Benz symbol around the center of the hoop, and you have to express your answer algebraically. You can only use m, L, and physical constants. So this is important because if you try to like define your own variables like lambda, you cannot put those into your final answer. If you do, they will take off points. They kind of like look for this in terms of like this. So what they want is just some algebraic expression that uses m and L as your two variables, and everything else has to be numbers, operations, and physical constants. And what we mean by physical constants are just like letters that represent a given number, and that applies to this question. Like, for example, G, if that applies 9.81 meters per second squared, that is a physical constant. Okay. So for rotational inertia, if you have certain, like if it's a composite and you have components, you can just sum those up and get your rotational inertia. So you have 3 components of rod and 1 component of hoop. So I would add those up. Now from part A, we had already demonstrated that the rotational inertia of the rods are ml squared over 2. So you can just use that information, multiply by 3, and add it to the rotational inertia of a hoop. Luckily for that, we do have a formula. It's ml squared. So you just add those, and we get I equals 5/2 of ml squared. Now, even if you couldn't do the integrals required in like part A to do part A, you could still do this problem because, again, part B just relies on information used in part A, and College Board does not expect you to be able to do all these questions in succession and all right. Okay, so the next part is that the hoop rod system is initially at rest and held in place, but it is free to rotate around its center. Now, a constant force F is exerted tangent to the hoop for a time. Let's call it delta T. And we are to derive an expression for the final angular speed omega of the hoop rod system. Now express your answer in terms of MLF delta T and physical constants as appropriate. Now you don't have to use all of these. It's just that if you can't use anything that's not these. So here we'll use kind of like the second law, but instead of like for linear motion, for motion like for in like one direction, in a one directional line, you will use it for angular motion, and the formula for that is T is equal to I alpha, and here alpha is angular acceleration, so that's delta W over delta T. No, sorry, not W, omega, which is angular speed. And over delta T, and then you move the delta T over, so you get torque times delta T is I times the rotational inertia we just found out, and then times omega 2 minus omega 1. Torque is force times distance, so that's Fr. And you can substitute that in, so we have Fr delta T is I omega. You can rearrange this equation to solve for omega, and omega is Fr delta T over I. R here is the same as L because the parts are connected. So omega is FL delta T over I. We know what I is, it's 5/2 of ml squared. So we can substitute that in for the denominator, and we get 2F delta T over 5 ml. Now you don't actually normally have to simplify completely if it's not necessary. So if you're a bit short on time, I feel like you can just express this 5/2 as like a decimal and you'll still be fine. Okay, now we have this wheel, the same wheel as the one we were trying to calculate, and it's moving without slipping along a level horizontal surface. Although at times t equals 0, let's say, the system begins rolling without slipping up a ramp, and we are trying to derive an expression for the change in height at the center of the hoop from the moment it reaches the bottom of the ramp until the moment it reaches its maximum height. Then express your answer in terms of ml, itote, and omega, and other physical constants. So how we do this is we use conservation of energy again, because it's a ramp, and we know that one of the starting points is at the ground, where there should be no potential energy in terms of like gravitational potential energy. So we will start with K1 when the thing is moving, equal to omega, it's equal to UG2, which is potential energy at the top. Now we have formulas for both of these. So here, you use 1/2 of mv squared for K1 and 1/2 of I omega squared for UG2, the gravitational energy, and you solve for the H as an MGH. So Here it was kind of like forgotten, but here there should also be a sum of mgh because there's also gravitational energy at the top, not just kinetic energy. So we will include that in as mg on the bottom for like um to for like the potential energy as being mgh. Simplify and we get this expression at the bottom. I'll highlight in red. I don't want to read this out, but okay, where is it? That's the answer. Now, the slice doesn't work, so I'll stop sharing for now as I pull up this slide. Let me see. Oh, well, it looks like um the slide finished. So I guess we can go onto the College Board website and like tinker a little bit more with this. Now, College Board doesn't really give multiple choice, so I apologize. I can't really provide good like examples of multiple choice, but they do have the list of free responses just on their website. So all you have to do is let me share my screen. Just type in College Board AP Physics C pass FRQ, which is just shorthand for free response questions. And we will get the first link you will get is just past exams questions from APC Physics C Mechanics. And we have all of them. That it basically goes all the way back to when they started the exam. So you can always go here and look for answers. Um, the free response questions are scored by points, like each part has like unequal amounts of points, and depending on how satisfactory or how thorough you write your answer, you can get like different amounts of points. Normally the average is very, very low for these questions. Like it doesn't normally go around above 5 out of 15 for each, but you should still try on these questions. So let's take a look at one of the questions we did. So you open this up, you'll get your formula sheet. So this is for all of physics C, not just mechanics. You have electromagnetic stuff as well, such as like electron volt, electron charge, and stuff like that. But we're not going to get into that now. Um, you also have obviously mechanics stuff. Like this entire left side is your mechanics formula, and this entire right hand side is the E&M formulas. If you want, we actually can stop here and I can go over each and every one of these equations if you want to know them. Do you guys want to try? Do you guys want to do that? Um, okay, so I'll try to like dumb these questions down a bit, since you can see there's quite a bit of like calculus in like some of these formulas. But in the end, these are actually just for mechanics for the most part. E&M is completely different, but for mechanics mostly, it's just physics one stuff. Um, but it's just like it's just spiced up a bit. So you are probably familiar with these equations on top. These equations are your basic kinematic equations. So this first one is stating that V final is V initial plus AT, which is probably something you know from basic physics or kinematics and basic physics 1. that basically states that if you're traveling with a constant acceleration, your acceleration times time is your change in velocity. Uh, your next one is relating displacement to your initial velocity and acceleration. That's basically your x, your displacement is equal to your initial displacement plus b initial t plus 1/2 of at squared. This one is also taught in physics 1. It's not really written out like this. I'm pretty sure it's just written as delta x is equal to v0t plus 1/2 of at squared. But I could be wrong on that, and it's this exact same equation. Here is probably the ones that's a bit harder to remember, but it's pretty cool in terms of like you don't have to like solve this. You don't have to solve these two to get like v final from v initial. If you know your v initial, your change in displacement and your acceleration, you can find v final by this equation where um, the difference in squares between the velocities is just 2 times a times delta x. This equation down here is Newton's second law, F equals ma. Although F here does not actually reference like a single force, it references total force in the system, which is why they kind of call it F net instead of ma. This is just sigma notation, just saying it's the total force or net force. These two are they mean the exact same thing. F net is equal to ma. You probably know that equation because physics 1 does this as well. This was Newton's original way of stating his second law, and that is basically force is the derivative of momentum, or basically it's the change in momentum over the change in time. Now, as we kind of like talked about in the first problem, there's an impulse momentum equation where the impulse is basically just your change in momentum, and impulse is also equal to force times time. So here's just like one way of stating it. dp over dt is it. You can think about like you can think about it as like the rate of change in like a certain moment, like an infinitesimally small, like elapsed amount of time. If since as you can see down here, the definition of momentum is mv. If you just do, if you do dp over dt, you would just do like since mass is a scalar, you literally just have m delta v over delta t. Then delta v over delta t is a acceleration. So it's literally just saying f equals ma, just in a different format. Although you can also think about this as defining what impulse is. Here is again your impulse momentum equation stated in full. The reason we have an integral here is because force, as we saw in that last problem, does not have to be constant. And if your force is given as a function with respect to time, you have to integrate it. And then J is your standard symbol for impulse. This one is P equals mv. This one is also taught in physics 1. It didn't change at all. I think this one's pretty self-explanatory, so I'm not going to go over it. This equation is stating that the maximum amount of friction you can have is your friction coefficient times your natural force. So this little f stands for friction, and this big N stands for normal force. So it's basically just stating that the max friction has to be equal to the friction coefficient, which you're normally just given or have to solve for, times N. This coefficient, there's like a warning in between, like because they will give you two different moves. That's the symbol. One should be for static friction and one should be for kinetic friction, and they're separate and should not be used with respect to each other. Static friction is basically when the object is not moving. You need a greater amount of force to actually get the object to begin to move. Then kinetic friction is when the object is already moving and it's just friction to just slow down the object. So static friction would the coefficient would be written as mu s. Then for kinetic friction, that will be written as mu k. The next one is your work kinetic energy theorem, which basically states that your change in kinetic energy is equal to your work. Then work itself is integral of force with respect to distance. In physics one, since force is always constant, um, that would basically be just Fr or Fd. Actually, it should be Fd. So this delta should be referencing kinetic energy. It's equal to your work. Um, this equation is very important if you actually want to take the exam, since I don't know. I feel that from what I've seen, the test makers like this equation a lot, since it proves as a very useful shortcut at times if you're trying to solve stuff, and it can take a lot of time if you actually don't know this one. The next one is just definition of kinetic energy. It's 1/2 mv squared. Um, Power, which is measured in watts, is equal to is basically equal to your derivative of your energy function. This one you don't really need to know at all for the most part. Very rarely does the exam ask for power. Although it's more useful to know that that E in energy what stands for work. You have to get a work value first, or like a work function by integrating the force function before you can do this part. P, since it's dE over dt, and then E could roughly be said as like FD. Basically, that's kind of like saying P is just FdV dt. Not dV dt, dd, derivative of distance over time. The derivative of distance or distance over time is equal to velocity. So there you go. There's your second way of trying to find out what power is. This one is just your definition for potential gravitational energy. That's UG is equal to mgh. Delta H is there to reference the fact that the ground may not actually be at ground level. It might be a bit elevated where you're just trying to find the height between the height differences and not actually trying to find like the distance to the ground if like the point you're trying to like measure is above the ground. So you have that. Um, this is your definition of centripetal acceleration. This one is just best to memorize it. There's no way I can't really go around that. Omega c is is equal to v squared over r, where v is called your linear speed. Your speed you go if you're traveling in a straight line, and your car is wait, what was I saying? Oh wait, your omega is your angular speed. So that's the same thing as v over r. These two again are the exact same in definition and math. Um, Pretty important to know as well. Okay, the next one is how to find elastic potential energy. I'm here where it says US here. That's just the definition of elastic potential energy. You kind of just have to get used to it. Again, that's like one of the questions where you just memorize it. It's pretty self-explanatory. Here is saying that your FS, which if I believe correctly, is your force from I don't remember. We'll go into that later. I'm pretty sure this is your force from the spring, and this is equal to negative kx, where x is basically the length that the stream has compressed. This is known as Hooke's law. Okay, torque is equal to the cross product between um, R and F. Now, in most cases, that angle between the two vectors would be right, so you don't really have to worry about that at all. But um, later on, you probably do have to worry about that. This is basically the cross product vector is basically just formatted as, if I remember correctly, as F, where F stands for force, D is displacement, if I remember correctly, and the last one is just security. Uh, Um, it's just security to make sure that like if it's pulled at an angle, you can still have a feasible way to calculate it, and that's by just including the sine of that angle, and then just multiplying that on, tacking it on to create like your formula for torque. For most cases, it's just if you have some random sigma moving in circular motion. Uh, let's see. That's horrible. Undo. You have something traveling in a circle. Uh, really, if this is like, for example, if this is your force vector, however unlikely that is, all you have to do is just draw a right triangle and just find the interval for the side. Now, so here you have this perpendicular side, and this is like your main one that what you'll be trying to count if you were in this scenario. That would just be this side times the sine of this angle. So that explains like the presence of a trigonometric equation. We're on our last section for the most part, and most of these are simple harmonic and gravitation stuff. These are also not tested as much, although they still are tested. And they could be pretty difficult if you don't pay attention before the exam. So basically, let's start with x equals x mass cos omega t plus phi. That's your basic standard harmonic equation. X here would kind of like mean your y in a coordinate system, and then x max is the amplitude of oscillation. If you don't know what that is, you can go to the Logistem YouTube channel. I'm pretty sure there's couple of briefs that talk about oscillations, and you can learn what amplitude is there. It's x max, and then cosine references the fact that oscillation on a graph is kind of like a sinusoid. It's like a wave formation. So you have to use one of the trigonometric functions here. Cosine is used. And then inside is omega t, omega's angular speed. Remember that? Then plus this is called your phase constant. It's a very weird number, but it dictates by how much left or right should your thing switch. So it should like the equation start off on, because it could seriously like impact like the actual graph if it were like slipped or incorrectly recorded too quickly. Which one is next? Here you have your restatement of like your Newton's second law, but instead with Turkey. Wait, no. I was thinking about where this came from. No, it's equal to T net, as T net is equal to IA, I alpha, where basically I is the moment of inertia, and then alpha is your angular acceleration. So your net torque is equal to I alpha. Now, This is kind of just a restatement of your F net equals ma. Imagine like everything was constant, right? So T, your torque would just be Fr, F times R. Uh, your I would be um, mr squared, and then your A would be an A over R. So your in general, actually, a lot of the properties you can say that that force and kinematics have are shared with angles. You just have to convert them into the correct like variable system. So for force, for example, you cannot just talk about like torque like Newton meters normally. Um, okay, so the next one is your period functions. So the period is defined as 2 pi over L. I forgot which country uh, invented that. So whatever, we're just gonna skip that. Well, it's also equal to 2 pi over the angular frequency, omega, which is pretty big. But more importantly, T is equal to 1 over F, where F is the frequency. That's basically the main definition. Now, if you use differential equations and solve it, it's very complicated. We won't get it. We won't get into it here. You would find out that T for a special pendulum is 2 pi root m over k. Um, your top one, your top period function under like T equals IF, that's your one for one of the types of springs, and the other one's for the other. G stands for gravitational, and we would just kind of stands for impressive. Okay, so um, so here are kind of like examples at the bottom page of omega, and how similar it is to basically the kinematic system. At the bottom of the page, aside from like the period stuff, you have I is equal to the integral r squared dm. It's pretty straightforward. We kind of talked about it before. Um, okay, well, I was trying to think about like a good way to present this, but since we're a bit short on time, I guess I'll just talk about it in general. Then the program will end for today. So FG is your universal gravitation. That's basically, that comes from the fact that every single object with mass has a gravitational force associated with it. And your formula is big G m1 m2 over r squared, where that's basically Newton's law of universal gravitation, where m1 and m2 are two people or two objects with um, some mass that eventually has some gravity. And then the other type that's not a what matters is kind of like your rug stuff. So that would see, that doesn't impact that much. So for the springs, the formula for period is just 2 pi root m over k. Again, no real way to memorize that for me. I found it difficult to memorize. Just pay attention, I guess. And for the next one, that references potential energy and not even that doesn't reference universal gravitation. That references universal potential energy, where potential energy and at a distance infinitely far away is zero, and all normal potential energy other than that is negative.